Okay, so the topic for today's discussion is discrete time systems. The topic for the continuous time systems is over. So I'm just going to solve or just give you some ideas about how do you get stability, the modes of the system, stability of the system, controllability, observability of the systems, and then control system design for discrete time systems. We have about 4 classes left. I have to upload the last assignment. I'm going to do that either today or tomorrow. It's not going to be a long assignment, so hopefully you'll be able to do it by the end of the semester, which is next week. And the projects are supposed to be due, I think, the week after that, but I could be wrong. Maybe it's next week, Saturday. So so I think the project is also due. The homework is also going to be due next week. So hopefully everything that you need to do for this class will be done by the end of next week, and I'll do the final grading. If you have any questions, feel free to reach out to me the week after next. Okay, so in the next 4 classes, I'm going to talk about discrete time linear systems. To motivate the discussion, there are some systems that are inherently discrete, and then there are analog systems that you are sampling at discrete intervals, and therefore it becomes a discrete time system. So, what are the systems that are inherently discrete? If you think about banking system or financial system, they are inherently discrete. If you look at your, I don't know how many of you have mortgage or how many of you have bank account that pays you interest. But if you have mortgage or bank account that pays you interest, the interest is calculated at the end of the day. So in some sense, um, it's not like you are getting an interest for every second or for every millisecond that your money is in the bank. You get an interest for every day that your money is in the bank. So that's an inherently discrete time system. In biology, there are species that reproduce or hatch at a very specific time. So if you want to look at the population of that particular organism or that particular insect or that particular species, it's an inherently discrete time system. Okay. Um, Naturally, so that's those are the situations where the system inherently is discrete time. Inventory management is also inherently discrete time system. So you don't manage it on a millisecond by millisecond basis or microsecond by microsecond basis. You're doing it on a daily basis. So there is inherent discreteness in the time axis. Um, the other classes of systems are analog systems. So going back into the history, if you are in 1950s, everything is analog. Okay, there's nothing discrete. You don't do any sampling because there are no computers, there are no microcontrollers. Now let's go to 1970s, and the first few microcontrollers were created at that time. And if I'm not mistaken, I think Intel was the world leader at that point of time in creating discrete time systems. But I could be wrong. Maybe there were a bunch of companies that were creating microcontrollers and devices with discrete times, which can potentially do cool things in 1970s. So in those cases, what happened was this was the sort of architecture. So you have digital to analog converter that goes into your LTI system, which is x dot t equals to axt plus but, and then you have yt equals to cxt plus dut. The output yt, this is my ut, this goes into analog to digital converter. What you get is ytk, which is sampled at time tk. That then goes into, I'm going to make this block bigger. This information will be fed to a microcontroller. then programmable logic controller, then CPU, GPU, and so on, depending on the dimension of YTK, and then that then computes UTK, which then goes back into the digital to analog device and then gets fed back into the LTI system. So this is the situation that emerged. This is the architecture that kind of emerged in 1970s, and it remains a dominant way of doing things in today's world. So this is sampled at time tk. Anybody knows how do you convert UTK, which is a discrete signal, into a continuous time signal? Any ideas, any thoughts? You have a discrete time signal, you want to convert it into a continuous time signal, what would you do? Any ideas? No? Well, what you do is called zero order hold. Where UT is equal to UT naught, T naught less than equal to T less than T1, UT1, T1 less than equal to T less than T2, UT3, sorry, T2, and so on. So this is a zero order hold. So whatever is the U at the beginning of the time duration, you keep it the same until the end of the time duration, T0 to T1 and T1 to T2 and so on. Okay, let's look at an autonomous vehicle situation. So you have an autonomous vehicle. That autonomous vehicle is working in continuous time. You have cameras and lidars, which is looking at making the observation YT, which is about what's happening outside the vehicle, what's happening on the road. It's sampled at time tk, and then YTK, which is a very high dimensional observation of what's happening around you. It goes into, in the case of an autonomous vehicle, it goes into a GPU because the data is pretty high dimensional. You have cameras, you have LiDAR, you have radar. So all of that information goes into GPU. Then within GPU, of course, there is localization, identification, localization, a lot of other computation that happens. And then the planning, after the planning is done, then the next control action is deduced or it's computed based on some algorithm, and then that goes into the digital to analog device. Let's say the engine RPM or the braking action is what the control action is, then it gets converted into a continuous time signal that then gets implemented on the vehicle. Okay, so that's roughly what the architecture is. And the most important thing I want you to remember is the zero order hold. You can have first order hold, in which case you interpolate between UT0 and UT1, and then you interpolate between UT1 and UT2, like a linear interpolation. And that's how you compute the UT. And you could have second order hold, in which case you take a spline interpolation between these three variables, and that's how you determine what ut is. I think the first order hold, second order hold, and all that, like higher order systems, I'm not sure who uses that, but I know that in signal processing, people tend to study those kind of situations where how do you convert a discrete signal into a continuous signal. But in control systems, because you don't have information about the future, you tend to use zero order hold, and that seems to be doing well in the world. So why do make our life complicate and just keep using zero order hold until we encounter a situation where we have to predict what the future is going to look like. So anyways, right now zero order hold is what we need to do and what we will study, knowing well that linear interpolation, spline interpolation, and other techniques do exist, but it's used in signal processing but not in controls. Any questions so far on this diagram? I think this is fairly easy to understand. Now, what's the model of the system? What's the discrete time model of the system? So the system generally is written as x k plus 1 equals to axk. Oh, let me use the time varying system first. Even though we are going to study time invariant for most of the class, this is my linear time varying discrete time system. Okay, yes, please.
I have two quick questions from the diagram.
Right, yes, yes, please.
So the zero order hold is basically being implemented in the DAC, right?
In the digital to analog, yeah, digital to analog.
So in the analog to digital converter, you said it's samples, right?
Yeah.
So what is that process called? I understand like
it's just sampling.
You just sample, right?
Yeah, you are just sampling. That's right. That's right.
Sampling rate.
Correct.
But it's just called sampling.
It's just sampling. Yeah. There's no complicated science there in that particular thing.
Zero order hold, is that related to Z transform? Or?
Not quite. Not quite. Z transform, I know that Z transform is not the topic here, but Z transform is essentially Laplace transform equivalent in the discrete time situation. But it has nothing to do with zero order hold. There is some, you might have something to do with it if you are looking at Z transform of the original discrete time signal and the Laplace transform of the continuous time signal. So there is some connection there, but that's not part of the syllabus, but there are books that talks about it. Okay, it's not too different, it's not too difficult, but yeah, I don't want to go on a tangent here. Any other question? You had two questions, right?
The second
oh, I see. Okay, it's okay, perfect. Awesome. So things that are inherently discrete time, like banking, financial sector, biology, and so on, you can write it in this particular format. You can figure out what AK, BK, CK, and DK matrix looks like based on the physics, chemistry, biology, or regulation. But I want to go to the continuous time system and try to reconstruct what this matrix is going to look like in the case where you are doing the sampling for a continuous time system. So what is the continuous time system? I have and I have yt equals to ct xt plus dt ut. Let me just do it for the xt case, and then yt would be very simple and straightforward because all you're doing is sampling. Uh, so let's see. Let's say the sampling time t0, t1, tk plus 1, and so on. So remember, there is a strict inequality here. So it's not like you can sample at the same time. You are essentially having some duration between t0 and t1, after which you are doing the sampling. Okay. Generally speaking, you could have sampling where tk actually equals to kt, and t is called the sampling time. Oh, but capital T is also used for other things. Uh, Tau is used as an integral variable, so I can't use tau. How about I pick t bar? Let me use t bar. So t bar is the sampling time. Generally speaking, sampling time could be 1 millisecond, 100 millisecond, 1 year, and so on. In biology, if you're looking at, what's the population of bears, for instance. So bears are not really changing on a daily basis, but on a yearly basis, they are changing. The numbers of bears are changing due to death as well as due to births. So generally speaking, in those cases, you will have the sampling time of the order of a year. But if you have insects, the sampling time would be of the order of a day. I'm not sure, but I think mosquitoes live only for 1 day. Like the entire lifetime of mosquito is just 1 day or maybe 2 days. So if you're looking at mosquito population, if that's what your control, I mean, that's your state variable, and you want to control the number of mosquitoes in an area for whatever reason because you want to prevent some disease or whatever, then in that case your sampling rate should be probably 1 day. Okay, that's what is going to drive the population of the mosquitoes. And in cars, I think most of the things are sampled at 50 milliseconds scale, 50 or 100 milliseconds, but you could have things like engine rpm, and that would be at a millisecond or zero point 0.1 millisecond scale. So depending on the process, depending on the application, you will have completely different sampling times. Okay. So I have a continuous time system. So I'm running a car engine, I'm running an aircraft, I'm running a quadrotor, I'm running a washing machine. These are all continuous time systems. It has motors in it, it has a bunch of actuators in it. But I'm actually wanting to control things digitally, so I have to convert it into a discrete time system. So if you remember, my xt in the continuous time is given by phi t naught x naught, and this is known as the state transition matrix. And then there is this integral of t naught to t phi t tau bt b tau u tau d tau. Right, this is my state transition matrix. This is how I compute xt. This was actually covered in lecture maybe 4 or 5, I think. That's when we covered this expression. So if you go back to lecture 4, we have derived this expression from first principles by solving this differential equation. Okay. Now the question is given xt naught. So here is the question. Given x tk, find x tk plus 1. Who wants to do this? Okay, so let's do this. What is x tk plus 1? This is phi of tk plus 1 tk x tk integral tk to tk plus 1 Can someone tell me what is this u tau between tk and tk plus 1? What is u tau? So now this t naught is tk and this is tk plus 1. What's my u tau in that duration? Remember, we use zero order hold. So u tau is actually not going to change in this particular time interval, in this time interval. So this is actually going to be utk d tau. Okay, because this is a constant, utk is a constant, I can actually pull it out of the integral and I can write it as d tau utk and put this whole thing in a matrix format. I'm going to call this AK. I'm going to call this XK. I'm going to call this XK plus 1. I'm going to call this BK. I'm going to call this UK. And this is how I go from continuous time to discrete time. I'm going to pick CK to be CTK and DK to be DTK. And that's how I'm going to get the observation equation. Because I'm just sampling. So whatever is my CT, I'm sampling it at time TK. So that becomes my CK. And the same thing becomes my DK. This derivation is on page number 118119. So this is page 118119 of the book where all of this stuff is taken from. Okay, so what's the upshot here? You have a continuous time system. So you could have a system which is inherently discrete time, in which case you will find out this AK, BK, CK, DK matrix from the physics or chemistry or biology of that system. On the other hand, you could have a continuous time system like an aircraft that you're trying to control. So you need to discretize it in order to do that on a computer. So how do you discretize it? Well, you look at this expression using the state transition matrix. and you use that state transition matrix, put appropriate values in it, do appropriate integral in it, and you get the discrete time AK, BK, CK, and DK matrices, and be able to solve that particular problem, convert from one to another, and vice versa. Now the question is, this is still too complicated, but let's see what's a simplified version is. So simplified version, my A, B, C, D matrices are time invariant, so it's an LTI system, and my sampling time is T bar. So I'm sampling at very frequent whatever the interval is, and I'm sampling it exactly at that particular interval. So whenever my clock says 50 milliseconds, I do a sample. So what does that matrix AK, BK, CK, and DK looks like? So that's my question. While I erase the board, think about what is this matrix in case I have an LTI system and my sampling rate is T bar. So I'm not doing like random sampling times, but I have like a very specific sampling frequency at which I'm sampling. So first of all, what is this state transition matrix? What is phi of T naught in LTI case? It's exponential A T minus T naught. This is LTI case. So A is the matrix and T minus T naught, like because it's time invariant, I just have to take the difference in time, and that gives me phi of T comma T naught. Okay, so what is my AK? This is phi Tk plus 1 Tk, which is exponential A Tk plus 1, or this is K plus 1 T bar, Kt bar. This is exponential At bar. Does it depend on K? Does it depend on K? It does not depend on K. So in fact, AK is actually just a function of, well, okay, let me call it AD, discrete time. Let me call this AC, continuous time. So the discrete time A matrix is continuous time A matrix multiplied by T bar, and then you take the matrix exponential of that matrix. What is this roughly equal to? I plus AC T bar plus well, not approximately, that's exactly equal to this. So if T bar is small, I can ignore the higher order terms and I can just keep this term, but then that's an approximation. On the other hand, if T bar is large, then I can't really ignore the higher order term, so I have to make sure that I keep it in mind. Any questions so far? I think we covered a lot until now. We went from a continuous time system to a discrete time system. I'm using a lot of the machinery we developed in lecture 4, lecture 5, lecture 6, and so on. So I understand that you might have forgotten some of these things, but hopefully now that I'm talking about it, you will recall and fill in the gaps in your understanding. Any questions so far? Okay. So the way to get discrete time A matrix is using this particular expression. Awesome. Yes, please.
With exponential of AC t bar, suppose we send t bar to be very close to 0.
Right.
Does AD then approach I?
Very good question. So it doesn't approach I, it approaches I plus AC times t bar. So you can ignore the higher order term, but not the first order term itself.
So we just effectively don't take the limit as t bar approaches 0.
Yeah, you shouldn't take, you can take the limit, but only ignore the rest of the term, not the first order term. Keep that in mind. Because otherwise, there's no system that is stable.
Yeah.
Right? So if t bar is going to 0 and you think of this as the only point, then it's not stable at all. So that's not going to be the case. Good question, good catch. Any other question? Okay. Can someone tell me a system where t bar is very, very small? What is a system where your sampling rate is in gigahertz or something? Wi-Fi signals, right? We have 2.4 gigahertz and 5 gigahertz. So there t bar is of the order of nanoseconds. Okay. We have a router here, right there. So that's sampling at a nanosecond scale. Okay. Perfect. Okay, yeah, so solutions. So now that we are able to come up with a model, I do need BD. I need my BD. So what is my B of discrete time? That's going to be integral kt bar k plus 1 t bar exponential ACT minus oh, I see. Okay. This should be tk plus 1. Can you make the change here? This one should be tk plus 1. So this one is t, this one is tk plus 1. So I have k plus 1 t bar minus tau v d tau. In fact, I can do a change of variables and I can write it as integral 0 to t bar exponential AC. This b is also constant, so I can take it out. So this is AC t bar minus tau d tau times BC. This is BC. This is for the continuous time system. This is the discrete time system. Right, this is change of variables, the typical change of variables for the integral. So I replace tau by tau minus kt bar and I get this particular expression. Okay, so now we know how to go from continuous time system to discrete time system. Now let's look at what the solutions to the discrete time system is going to look like. So I'm going to do both the time varying as well as the time invariant discrete time system, and we'll look at what the solution to those systems looks like. Any questions so far? Okay. By the way, one thing you will notice is this also doesn't depend on tk, right, or tk plus 1. It's invariant of k. So this one leads to a time invariant system. So you start with an LTI continuous time system, you get an LTI discrete time system after using uniform sampling. So if your sampling rate changes, then of course you again have a time varying discrete time system, even though you started with an LTI system in continuous time. But because my sampling rate is the same, I'm using every t bar, I'm sampling the system at every t bar seconds. That's why I'm getting an LTI discrete time system. So homogeneous and well, let's try to look at the solution for LTV solution. So I have the system xk plus 1 equals to ak. Xk, I'm dropping the subscript c and d because now everything is going to be in discrete time, so there is no ad required. X of 0 is equal to x0. Okay, so let's look at what is x1. X1 is a0 x0. X2 is a1 x1 equals to a1 a0 x0 and so on. So what I get is xk plus 1 equals to phi k plus 1 L XL, where product J equals to L to K AJ. This derivation is on page 53 of the book. So this is the state transition matrix in the discrete time case. I'm using the same notation because it means the same thing. It's just that the domain is different now. The domain is discrete time. It's the set of integers, no longer it's a real number. Okay, so let's do it for xk plus 1. Suppose you have some other process driving the system, ak xk plus gk. So gk could be the control action, or gk could be some other external noise in the system. So in the case of air conditioning system, the weather outside serves as this driving force. for the internal temperature of the room. Has anyone driven up and down the mountains? Okay, so when you go up and down the mountain, the temperature also, the external temperature changes quite a lot. And so you could have a situation where you started with a very warm weather in the valley, and as you moved up the mountain, the temperature went down. So those are the variables that gets captured by this GK term. And now the question is, how does the state transition, how does the solution to this equation work? I can go over the same expression. So I get x1 equals to a0 x0 plus g0, x2 a1 x1 plus g1, which is a1 a0 x0 plus a1 g0 plus g1. And I can keep doing this, and I get xk plus 1 equals to phi k plus 1 L xl plus summation j equals to L to k oh, this should be j plus 1. J plus 1. I do want to add here that phi of kk should be identity matrix. So state transition in one time step should be the identity matrix. The other thing I want to note here is that if your L was equal to K0, which is the beginning of time, then I have xk plus 1 equals to homogeneous solution particular solution. And the way to get the particular solution is that you substitute L equals to K0. This is called the homogeneous solution. And this is particular solution. So homogeneous solution is because of the initial condition, and particular solution is due to the particular sequence of actions or environmental noise that was impacted or implied on that particular system. Okay, so particular solution is because of the external activity, and homogeneous is due to the internal activity within that particular system. So this is all the counterpart of the continuous time stuff that we talked about in lecture 4, 5, and 6. And this is the discrete time counterpart. One thing you will notice is that the expressions here are very easy because it's all matrix algebra. It's just matrix multiplication. And that simplifies a lot in discrete time system. In fact, I have always worked in discrete time systems. I don't work in continuous time systems because everything is simple. It's in the form of matrix multiplication. I don't have to keep track of matrix exponential and all kinds of complicated stuff. Okay. What happens if my matrix was time invariant? So my A doesn't depend on K. Can someone tell me how will these equations change if AK was equal to A for all K? What is my phi of K plus 1 comma L? What is this expression? So my this doesn't depend on K at all. I want to make sure, is it K plus 1 minus L or K minus L? It is K plus 1 minus L. You can substitute it everywhere accordingly and you will get the solution in the case of LTI system. Okay. So we talked about what all things have we done so far. We've talked about continuous time system. How do you discretize the continuous time system? We talked about the solutions to the linear time varying discrete time system, which is given in the form of the state transition matrix multiplied by the initial condition. And in the case of systems with an external input, you can do the same thing, but instead of the second integral that we had actually right here, you have now a summation equation where you multiply the input at time j with an appropriate value here, and then you add all the things up, and that's how you get the solution at time k plus 1. Now I want to talk about linear time invariant system. So in the case of linear time invariant, this equation simplifies quite a bit, and in which case my xk equals to a raised to k x0. So that simplifies things a lot. So now I can, if I want to understand the stability, if I want to understand the modes of the system, all I have to concentrate on is this matrix a raised to k. So let's study this particular system now. We will study the one with external input later on, but let's try to study this system. What I'm interested in is knowing how would the solution to this expression evolve. So I have an x naught, I'm given some initial condition, I'm multiplying it by a raised to k. I want to know whether this solution is going to die down, whether it's going to blow up, whether it's going to oscillate, like what is going to happen. Okay, so let's look into it. Look into this expression. Any questions so far? So our discussion on LTV is over. I'm not going to talk about LTV system again. No time variation. I'm just going to concentrate on time invariant system. Let's look at the following system. Xk plus 1 equals to 0, 1, 1, 0. Xk. What do you think is going to happen in this system? Any idea? Yeah.
Is A square gonna be null?
You can do the calculation. Yeah. Can someone want to comment on what's happening in this system? It's a discrete time system. I have this A, which is time invariant matrix. What are the eigenvalues of this matrix? Yeah, lambda equals to plus minus j. J is the square root of, oh, I've already used j as an index. Okay, so square root of minus 1. Okay. So I have a pair of complex poles, and in fact the complex poles lie on the imaginary axis. So you have plus j and negative j as the two poles of this particular system. What's happening to x1 and x2, like the two components of the state space? So what is x1 of k plus 1? This is my x2 of k, and x2 of k plus 1 equals to x1 of k. So actually it's just flipping. So if my x1 was x0 was 1 0, then my x1 0 1, or well, maybe I'll use something else, not zeros and ones, but maybe like 2 and 5, and this is 5 and 2, and then x2 is 2 and 5, and so on. So I'm just flipping. My elements are getting interchanged at every time step. Okay, so the poles, the eigenvalues of this A matrix has something to do with how the system is going to behave. Okay. It was the case in the continuous time as well. And so now, knowing this, we can probably think about how do we analyze the evolution of the state in this particular setting. How do you want to analyze this expression? So I'm given an initial condition. I have to multiply it by a matrix raised to k. That's what is going to give me the expression for x of k. I'm in 1970s. I don't have complicated computers to be able to run lots and lots of simulations of a raised to k and figure out what's going to happen. So how do I analyze this expression? What would your strategy be? I want to know what's qualitatively going to happen to xk. Okay, I don't want the exact numbers. I just want to understand qualitatively what's going to happen to xk. Is it going to go to 0? Is it going to go to infinity? In this particular situation, it's neither going to 0 nor is it going to infinity. It's in fact oscillating between two numbers. How would you analyze this? You have any thoughts?
Like checking its mode of the system.
Right. So I want to get to the mode of the system, but what's the step one for getting to the mode of the system? Calculating the eigenvalues. So what is that whole thing called? We do calculate the eigenvalue, but there is some
characteristic polynomial of the system.
Right. There's characteristic polynomial. Perfect. All the keywords are coming out. We'll do a similarity transformation of this particular equation. So what similarity transform? I'm going to pre-multiply and post-multiply by a matrix, and then transform the state space of this system into some other state space so that it's easier to analyze. Okay. So let's consider the case A is diagonalizable. We talked about this in lecture 10, I think. How do we diagonalize the matrix A? We have AVI equals to lambda IVI. I pick a matrix T, which is V1 Vn. I mean, we had a very detailed discussion in those lectures, lecture 7, 8, 9, 10, in order to get there. So I'm sort of compressing a couple of lectures here on the blackboard. So I have n distinct eigenvectors. I have n distinct eigenvectors. So I can stack all these eigenvectors as columns of this matrix T. What is my A times T? This is AV1, AVN, lambda 1 V1, lambda n Vn, T times lambda, where lambda is diagonal lambda 1 to lambda n. So this implies that A equals to T lambda T inverse, and this implies that A raised to K equals to T lambda raised to K T inverse. There are a few things hidden here. So is T invertible? Well, you have n distinct eigenvectors. So these are linearly independent set of eigenvectors. So therefore T has to be invertible because it's a full rank matrix. If it's a full rank matrix, then I can pick, I can take the T inverse, and so A can be written as T multiplied by a diagonal matrix multiplied by T inverse. Okay, what is lambda raised to K? What is lambda raised to K? It's each of the eigenvalues raised to K along the diagonal entries. So I can actually write it as summation lambda I raised to K, I equals 1 to n, T EI transpose T inverse. and these are the modes of the system. Or EI, all of you remember what EI is? EI is 0, 0, 1, 0, 0, 0, and this one is at the ith position. That's my EIth vector. So I'm using EI transpose here. Okay, so this entire thing was derived in the context of continuous time systems back in lecture 10. I'm doing the same train of thought for the discrete time system, except that instead of exponential of at, I now have a raised to k, and naturally a raised to k is much simpler than the exponential, so this derivation was much simpler in the context of discrete time system in comparison to the continuous time system. Okay, now when are the modes of the system going to be stable? What that means is, when is a raised to k going to die down? When will a raised to k go to 0? So if I look at this expression, I have something raised to k, and then I have a constant matrix, right? So I don't worry about this constant matrix, because I want to know whether a raised to k is going to die down, or whether a raised to k is going to go to infinity, or whether a raised to k is going to be constant. Okay, well, when is a raised to k going to be constant? When this whole thing is constant for all k. When is this whole thing going to be constant for all k? When lambda is equal to 1, right? So then everything is going to be constant. Okay. When is this going to die down? When is this going to go to 0?
Less than or closer to 0.
Right, but lambda could be a complex number, right? It doesn't have to be a real number. So in this case, my lambda is a complex number. So what happens when lambda is a complex number? You are right that if it is real number and less than 1, then this is going to go to 0. Well, not less than 1, but absolute value is less than 1, because it could be negative as well. But if it's a complex number, when is a complex number raised to k goes to 0 as k goes to infinity? When does that happen? Any idea? Okay, I think this is an important part. So let me spend some time on it. So the question is, okay, so let me pick j equals to square root of -1, and my complex number z is r e raised to j theta, right? Every complex number can be written in polar form in this particular fashion. Does that make sense? So what is z raised to k? Okay, well, this is given by r cos theta plus j r sine theta. This is from complex numbers class. You must have studied it back in undergrad, maybe 4 or 5 years ago. So what is my z raised to k? It's r raised to k e raised to j k theta is equal to r raised to k cos k theta plus j r raised to k sine k theta. So every complex number can be written in the polar form, and I can take the kth exponent of that complex number. In the polar form, this looks like this, which then expands to a value like this. So what's the absolute value of z raised to k? What is the absolute value of z raised to k? Anyone wants to give it a shot? No? I think this is very easy. Somebody should be able to answer this question. This is a graduate class, not an undergrad class. What's the absolute value of z raised to k? Okay, let me write it. It's r raised to k cos square k theta plus sine square k theta square root actually. What's cos square plus sine square? 1. This is r raised to k.
If you're taking square, right, so wouldn't the complex square would become -1?
You are right, but I'm not taking this square plus j times this square. I'm taking this square plus this square. J is not participating in the absolute value. Okay, so if you go back to your complex numbers class, if z equals to a plus jb, then absolute value of g is a square plus b square square root. That's how it's defined. Okay, that's how absolute value of a complex number is defined. Now, going back to the question, when is this complex number raised to k? When will it go to 0? So this is the number I'm interested in. I want to know whether a raised to k is going to die down, or whether a raised to k is going to oscillate, or whether a raised to k is going to blow up. That's my ultimate goal. So I've decomposed a raised to k in the matrix format, and I have term that is constant and a term that changes with k. So I want to analyze this term that changes with k. Now knowing this expression, under what conditions would lambda raised to k die down? Somebody wants to postulate, come up with a hypothesis. When is lambda raised to k going to die down? When is this going to go to 0? This will go to 0 when r is less than 1, because something less than 1 raised to k goes to 0, which means that the absolute value of lambda I has to be less than 1. And so the result, the theorem that we have, a raised to k goes to 0 if and only if absolute value of lambda I is less than 1 for all I. Okay, so what happens when lambda I, absolute value of lambda I is greater than 1? If absolute value of lambda I is greater than 1, then lambda I raised to k is going to blow up. So you have a situation where the absolute value is less than 1, then things are going to be stable, a raised to k is going to go to 0. If one of the absolute value is greater than 1, then things can blow up. And then if lambda i's are all equal to 1, then things will remain the same. Then there is a raised to k will not change. If absolute value of lambda I is equal to 1, as was the case in the example we saw earlier, the a raised to k will have some funny behavior where things are going to rotate, So not all the cases things are going to rotate, but you can imagine if each of these lambda i's have absolute value equal to 1, then you're essentially trading off energy from one part of the state to another part of the state and vice versa. Okay, so you're just moving energy in one form to another, chemical to electrical, electrical to chemical. That's the kind of stuff that might be happening. Okay. So when you have distinct eigenvalues of the A matrix, when A is diagonalizable, you have distinct eigenvectors, in which case A is, you can write A in this particular format, in which case the modes of the system is given by eigenvalue raised to k, which is a function of time, because time here is k, multiplied by this matrix. Now what happens when A is not diagonalizable? Okay, so that's the case 2. A is not diagonalizable. So we spent a lot of time when we were talking about continuous time systems in lecture 9 and 10 about Jordan canonical form. So in this case, we need to use generalized eigenvectors and use Jordan canonical form. Now it seems to me that people are tired in this class, so I'm not going to go through the Jordan canonical form thing. I'll give you the definition of the generalized eigenvector with the hope that some of you might go back and review stuff from lecture 9 and 10 so that we can recall and then we can have a more productive discussion in the next class. But basically, the generalized eigenvector, so let's say your A, the eigenvalues. So I'm looking at a simplest case. Eigenvalues of A are lambda, 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 n times. I have the same eigenvalue. But the null space of A minus lambda I has dimension 1. So my null space comprises of just one vector. I mean, a vector scaled by a scalar. So in this case, I have A minus lambda I v1 equals to 0, which means A v1 equals to lambda v1. And then, so this is the eigenvector. This is the eigenvector equation. And then I have generalized eigenvector. Where I pick A minus lambda I v2 equals to v1. I solve for v2, which gives me this expression. And then A minus lambda I v3 equals to v2, and so on. So v2, v3, v4, these are all generalized eigenvectors. So this means A minus lambda I square V2 equals to 0. This means A minus lambda I cube V3 equals to 0, and so on. So V1 satisfies this, V2 satisfies this, V3 satisfies this, and you can go on and construct n distinct vectors. It is known that these n distinct vectors are going to be linearly independent, and they form generalized eigenvectors of the matrix A. Okay. So I'll stop here today, even though we are slightly ahead of time. We'll stop here today. What I want to talk about is I'll take this equation as something that is given, and we'll construct the T matrix. We will construct the lambda matrix. So lambda is going to be in the Jordan canonical form. And then I'm going to go into this particular expression, and I'm going to dissect this expression, get what the modes of the system is going to be, and then talk about under what conditions would that mode go to 0 or that mode go to infinity. So we'll think about some of those stuff for the discrete time system, and then we'll talk about stability of the LTI discrete time system. So naturally, the question of stability is connected to the modes of the system. So we'll connect the two concepts, and we'll talk about under what conditions is a discrete time system stable, under what conditions it's not stable. That will be next class. And after stability, we'll talk about controllability and observability of discrete time systems. So the pace at which we are going, and if you don't ask me questions, we'll probably complete the whole syllabus of discrete time in like a couple of classes. So I do encourage you to ask questions and participate in the classroom discussion so that I can make sure that you guys are understanding whatever I'm doing on the board and not just being a passive listener. So thank you so much, and I'll see you on Thursday, right? Today is Tuesday, right? Okay, yeah, I'll see you on Thursday. Bye.